Hey guys, so up until this spot, we have learned how to take the derivative using the limit definition of the derivative, or the slope gradient formula. We've also learned how to evaluate the derivative at a specific point to return the slope of the tangent line at any given x along the curve. And then we also learned how to calculate the derivative using this guy and then compare it to the graph of the original by putting it in a graph page. Oops, that looks weird. So it'd be d dx of f1 of x. You pick it up using var, and then you check and see if the derivative you found lays right on top of the one the calculator found. Alright, so that's kind of all we know about derivatives so far, and what you're going to learn today is called the power rule, and it kind of makes this guy pretty obsolete because he's very clunky. So the power rule is a way to find the derivative of polynomials. So notice how visually what the function looks like is going to dictate the method that you use to take its derivative. So you see a polynomial, a radical, some rational, you'll see what I mean there. And constants. You can use these to take the derivative, or you can use the power rule to take the derivative of all four of these types. Sorry, moving a little slow today. I feel very sick. Okay, so dy dx is a noun. So once you've calculated the derivative and you are left with dy dx, that is the derivative of y with respect to x, and it would look something like this. Dy dx equals, and then whatever you found the derivative function to be. Whereas d dx is a verb. It's kind of like instructions. It's like take the derivative with respect to x of the expression that follows. So if you had something that looks like this, you would have to take the derivative of this. Then your answer is dy dx equals the derivative that you found. Okay? So there is something called the constant rule. And a constant function, so for example, a horizontal line that looks like y equals 5. It would look like something like this, right? Is a horizontal line whose slope is 0. Therefore, it follows that the derivative of a constant function is 0, because anywhere along the curve, his slope, or the slope of the tangent line at that spot, would be 0. Like if I tried to draw a tangent line right here, it would just have a slope of 0. So therefore, if c is an element of all reals, then the derivative of c, the derivative with respect to x of c, is going to equal 0. So I did a little proof over here. I used the limit definition of the derivative to find the derivative of something, f of x equals 5, something that would just be a horizontal line, right? So I started with the limit definition of the derivative function. And then f of x plus h, I usually do it off to the side. And f of x plus h tells me that everywhere I see an x, I'm going to put it in an x plus h. This guy has no x, so he would just end up being 5. That's where this ends up being 0. 0 divided by anything is just going to be 0, and that's why the slope of a constant is always going to be 0. Okay. Example 1, find the derivative of the following functions. So just visually, I see that all of these are functions, are constant functions. So I'm going to just play with the notation here now. So dy dx is going to be the derivative of y with respect to x of 8. 8 is a constant function, so the answer would be 0. F prime of x would be 0. S prime of t would be 0. And then dy dx of this guy here. You think he's maybe a variable, but k is a constant. And we know that pi squared is really just 3.1415 on, squared. So this guy's derivative would end up being 0 as well. Look at us, we didn't get scammed. So it is worth noting that functions for which the derivative exists are called differentiable. It means you are able to take the derivative of them. Some functions are differentiable at some x's, but not others. If the derivative does not exist at a value of c, we say it is not differentiable at c. Think about all the types of discontinuities that you learned about in the last unit. This is where you would kind of use your knowledge of those in order to say that, oh, we can't take the derivative of the curve at that point, but I can at other spots, okay? The power rule. if n is a real number and a is a constant in the function, f of x equals a times x to the n, then the derivative, so saying this is a polynomial, right? The derivative of the polynomial is going to be, whoa, hey there. The derivative of the polynomial is going to be where I take the exponent, I drop it down in front and multiply the constant that was already there by that exponent, and then I reduce the exponent by 1. This is in your formula booklet as this. So if you get to know that, you won't need it on the test. You'll just know. I see a polynomial or something that could be written as singular powers. I'm good. So in example 2, it says find the derivative of the following functions. So letter A visually is a polynomial. So if I wanted to find his derivative, I would use the power rule. Drop the 3 down in front. Reduce the power by 1. The derivative will be 6x squared. All right, let's do the next one. G prime of x. This one's a little funkier. Let's try to rewrite this guy so that way he is just a coefficient and a singular power of x. Then I can use the polynomial or the power rule. So now I would have 1/3 is the coefficient out front, and then x to the 1/3 is going to be my power. So now I have just a coefficient and a power. Now I can use the power rule. So that's what I mean by radicals can be used, or you can use the power rule with radicals. So now the derivative would be 1/3 times the exponent that you drop down in first, and then I have to subtract off a 1. But since I'm starting with a fraction, I'm going to rewrite the function as 3/3, so that way they have a matching denominator, and I would just get negative 2/3. So out of g prime of x is equal to 1/9 x to the negative 2/3, and you could rewrite that as a power or as a radical if you would like. So I'd have g prime of x is equal to, there's just a plain old 1 out in the front, and then in the denominator we have a 9, and then the cube root of x squared. Okay, for the next one, I would like to rewrite the next one as a singular. I'm going to do it in a different color so you can see the work for it. I'm going to try to rewrite it as a singular coefficient and power. So he is in the denominator, and I want to bring him up top. So I would rewrite this as y equals, and then I would have 5/3 times x to the negative pi. Okay, so now I have a power, then a coefficient out front. Now I can use the power rule. So I have y is equal to negative 5/3 times x to the negative pi minus 1. And if I wanted to make that, sorry, that's the derivative. And if I wanted to make that power positive, I would just write it as such. So I would have negative 5/3 times, if I kind of pulled up, let's try to figure out what this guy would look like. So I have x to the negative pi plus 1. Okay, so when he becomes positive and he goes down into the derivative, he'll look like this. All right, cool. And then let's look at this one over here. So I want to kind of rewrite him as just a coefficient and a power of x. So I've got 6 out front, and then I have x to the, and then this guy is going to be 3/5, roots in the ground, powers in the sky, and then he is down in the denominator, so he's negative. And now I can use my math. If I wanted to rewrite him as a radical, which is great practice, by the way. All right, it would look like that. Okay, example 3. Rewrite, evaluate, aka differentiate. That means take the derivative of and then simplify the following. These are just the same. Oh, I got an email. These are just the same as the other ones that I was doing above. Okay. So I would have d dx of 5 over 2 x to the negative rad 2. And then if I wanted to take the derivative of this guy, I would end up getting 5. It's a negative out front, rad 2 over 2 x to the negative rad 2 minus 1. All right, let's do this one. I'm not simplifying them. I gotta simplify them. Okay, sure. I got negative 5 rad 2 up top, and then I've got 2, and then I would factor out that negative, and it would be rad 2 plus 1. Okay, 2x to the rad 2 plus 1. All right. Sorry, it's a little squishy. Okay, so this one is a little sneaky because if I rewrote this guy where I have to bring this whole piece up from the denominator, so it's going to be 2x to the negative third when I bring him up, okay, because the 2 and the x are grouped together in parentheses. So now I can only deal with a singular power or a singular coefficient out front, so I would have 4 times 2 to the negative third times x to the negative third, and now I could take the derivative. So I would have negative 3 times 4 times, I'm just going to drop the 2 out, 2 to the negative third down here. Alright, times x to the negative fourth. Okay, so now I've got dy dx is equal to, I took the derivative here, is equal to negative 12 over 8. That could simplify x to the fourth. So then this would be negative 3. So negative 3 over 2x to the fourth. Alright, cool. So then for the next one, I'm going to do this one up here. This is a little sneaky because I want to combine these t's into singular powers of t's. So remember that when you divide like bases, you subtract the exponents. So I'd really have t to the first minus t to the 1/2. So I get t to the 1/2. That's the starting power up here. Then when I take the derivative, I would end up getting, where's my thing? Oh, 7 over 6. T to the 1/2 minus 2 over 2 dy dt is equal to 7. This guy's going to end up being negative. Okay, 7 over 6, and then this would end up being negative 1/2. We're t down in the denominator. Alright, so these are our answers here. We've got this. We've got this. If you're doing these on your own and you want to kind of check and see if yours is the same as mine, but it could be a different, could look a different way, you could always graph what you got and see if it's the same as mine by graphing them on top of one another. Okay, so this is d dm. Take the derivative with respect to m. So then I would have 6 times 3 to the negative second times m to the negative second. So 6 over 9 m to the negative second. Alright, I'm ready to go. So now, actually this can reduce at 2/3. Okay. Now I'm going to take the derivative. Alright, so I got negative 4 over 3 m to the negative third dy dm is equal to negative 4 over 3 m cubed. Alright, cool. Example number 4. It says find the derivative of the following functions. Alright, so these are just polynomials. I'm not rewriting them with radicals because the other ones up here had radicals, but then example 4 doesn't. So maybe we should name these. These are like radicals. What was example 2? Kind of everything. Or trying to rewrite with singular coefficient and power of x. All right. And then example 4, it says find the derivative of the following functions. Okay, so I only know how to take the derivative of polynomials at this stage in the game. So you should be looking at this one and this one and be like, I'm going to have to do some algebraic manipulation to get that thing into a form where I can actually take the derivative of it. Okay, so I would have f prime of x is equal to 3x squared minus 4, and then that's it. That one was easy. All right. That was for A. I'm going to put B over here too because I feel like I'm going to need this space, okay? So I'm just going to rewrite g of x, so it's just a coefficient out front and a singular power of x, then I'll take the derivative. So here I would have negative 1/2 x to the 4th plus 2x to the 3rd minus 5x. And make sure you keep your notation straight because it's hard to tell if you took the derivative or not if you don't write it out as like, okay, this is my rewrite of g of x, here it is, and then you take the derivative. I feel like that's the number one mistake like kids do with these. And then now I just rewrite it, easy peasy. Okay. Alright, so now let's start C. So I see that C has stuff in the top and stuff in the bottom. So I know that I can rewrite this as a power of 2x to the 1/2. And then I see that there's an x here, an x here, an x here, and then we'll figure out what's going on with that one. What I'm going to do is I'm going to separate each term across the pluses and minuses because I am okay to do that. It's kind of like decomposing the numerator in a fraction. You know, when you try to get a common denominator, you're like, oh, 1/5 minus 1/4. You get the common denominator. And then you kind of combine these up here. Yeah, you're doing the exact same thing, but you're kind of decompressing it. You're splitting negative 1/20 up into this 4 minus 5/20, okay, which is like kind of confusing, I guess. I don't know. Maybe that was a more confusing explanation than before. Let's do one together and see if you know what I mean. So y is equal to, I now have 2x to the 3rd over 2 rad x. You see I'm like decomposing numerator over denominator. Okay. Now I'm going to try to get singular coefficient out front and combine the powers of x. So I would be starting with, note my notation, I'm still y equals, I haven't taken the derivative of anything yet. The 2's would cancel and I would get x to the 3 minus 1/2, so that would be 6 over 2. 3 minus 1/2 would be 6 over 2 minus 1/2, which would be 5 over 2. Minus, and then here I would get 3 over 2 out front, and then the x's would combine, I would get 2 minus 1/2, which would end up being 1 1/2, which is 3/2. Plus, and then I would have 7 over 2 out front, and then x to the 1st minus 1/2 would give me x to the 1/2, and then plus 5 over 2, and then I would just rewrite him as x to the negative 1/2. Alright, so that kind of, the minus sign disappeared a little bit. Kind of did it again. But now I'm taking the derivative, and I would have 5 over 2 x to the 5 over 2 minus 2 over 2 gives me 3 over 2 minus 3 over 2 x to the 3 over 2 minus 2 over 2 gives me 1 over 2 plus, and then oh wait, I didn't multiply that guy when I was going through. Hang on. This first one, this piece here is right, and then now I would have 3 over 2 times, I forgot to drop the exponent down in the front. Minus 1/2, or minus 2 over 2 would give me 1/2. Okay. Okay, I'm going to have 7 over 2 times 1/2 x to the 1/2 minus 2 over 2 gives me negative 1/2 plus 5 over 2 times negative 1/2 x to the negative 1/2 minus 2 over 2 equals negative 3 over 2. Okay, yikes. So now I'm going to have 5 over 2 times the square root of x cubed minus 9 over 4, and then use just a plain old square root of x, plus 7 over 4. Oh, that x to the negative 1/2 is going to go down in the denominator with the 4. Plus, oh, he's negative because he's 5 times negative 1. Okay, so we would have negative 5 over 4 x to the negative 3 over 2. Negative 3 over 2. Negative 3 over 2 is going to go down in the denominator. He's going to be the square root of x cubed. Alright, looks good. And then for the next one here, I'm going to rewrite him as a polynomial. And the way I have to do that is by expanding. So now I would have 3x plus 2 times 3x plus 2. I would double distribute that, then distribute the x. So again, 9x squared plus 6x plus 6x plus 4. Notice how I'm still y equals, so now I've got 9x squared plus 12x plus 4. Now I have 9x cubed plus 12x squared plus 4x, and now I take the derivative. Alright, yay, we're almost there. It won't let me select the highlighter. Oh, don't freeze on me. Hey, you want to talk for a second? Even though I'm sick and I had a bad weekend, I did get a new puppy, which is really exciting. Please stop freezing. Okay, maybe I can just kind of... I'll show you guys my puppy when I get back in. Okay, come on. Ugh. Come on.